welcome to Tolleson Physics. So what we're going to look at today is how we can look at an object that is traveling under the acceleration due to Earth's gravity. We're going to add some additional forces in there to propel the object into upward first. So we're going to look at vertical forces and then see how the force due to gravity, the acceleration specifically due to gravity, can then affect things. All right, so with our first problem here, what we're going to do is we're going to look at a model rocket. So a 250-gram model rocket that we're going to launch straight up in the air. The propellant itself is known to have about 4 newtons of force, and then it stays on for 2 seconds. So let's determine how high the rocket travels while the engine is firing. We will also end up figuring out how fast it's going. We're going to need that for some other problem solving we're going to do with this. We're going to assume there's no air resistance, so what we're going to have is we're going to have 2 forces on this rocket. So let's draw a force diagram first since I have that information. So I know, according to this, that the upward force, which is a thrust force, I'm not going to write that out because it's cluttered, but that thrust force is 4 newtons. At the same time, the rocket has a weight, right? So its mass is 250 grams, which is the same as 0.25 kilograms. Just remember, kilo means 1,000. So multiply that by 10, you get 2.5 newtons is the downward force. So how do I figure out the acceleration on this? Well, I use Newton's second law once again, right? F net divided by the mass. So in this case, it's accelerating upward. It's starting at a rest on the ground, and then it's going to fly upward. And so the up force is 4 newtons, the down force is 2.5 newtons, and we're going to divide that by the mass in kilograms, which is 0.25. All right, so what this ends up being is what, 1.5 newtons divided by 0.25 kilograms. And so when we solve for that, 1.5 divided by 0.25 is 6. All right, so we get 6 meters per second squared. So we want to know how high the rocket goes. So this is where velocity time graph comes into play, because we want to know the area. And so let's draw the velocity time graph over here. We're starting at a rest and we're speeding up. We know the slope of the line is 6 meters per second squared. And what else? We know that it takes 2 seconds. So once again, I'm going to start with the idea of the slope is the acceleration, which is the change in velocity divided by change in time. Since I know the time and I want to know the velocity, I'm gonna multiply, cross multiply, so I get acceleration times time. And so in this particular case, the acceleration is 6 meters per second squared, and the time is 2 seconds. So that final velocity when the rocket is done firing is 12 meters per second in the upward direction. We want to know how far it goes, so let's then think about the area, right? We want to know this area here. So the distance that it travels is going to be the area, which is a triangle in this case, so 1/2 base times height. So let's put in the numbers that we know. So 1/2, the base is 2. So the starting velocity that we found over here, the ending velocity actually was 12 meters per second. And so 2 seconds divided by 2 is 1 second. The seconds cancel, and you end up with a distance that it travels of 12 meters. So when the rocket shuts off, the force diagram changes. And that force diagram just becomes the force due to gravity, which is 2.5 newtons. Right? I could calculate the acceleration, and I'll go ahead and do it. It's not necessary because we actually know what the acceleration on Earth is. It's 10. But here's proof of that, right? 2.5 newtons, and it's 0.25 kilograms. And so when I take this divided by that, I do in fact get back what is the gravitational constant on Earth. All right, now what the question is asking is how much higher does it go? So on the previous problem, it already went 6 meters. So how much higher is it going to go? So to answer that, I got to think about, oh, when it gets up to the top, what's the speed when it turns around? And so the speed or velocity in that case is going to be 0. So we can draw a velocity time graph that shows that. So velocity time. right? So I'm going to start from before, and actually I rewrote it right there as well, is it was 12 meters per second, right, when the rocket engine turned off. So it's going to keep going up. So I have a positive velocity graph. And so it's going to keep going up until it turns around. And here's the turnaround point when the velocity is 0. After that, it's going to fall down. Okay, so what do we know? We know that the height before it was 12, that doesn't matter. So I've got this and I've got the slope, right? So the slope is 10 meters per second squared. So let's do something with the slope first. Right? Slope is acceleration, change in velocity divided by change in time. What do I want to know? I guess it looks like I'm going to solve for time. And so that's velocity divided by acceleration. So 12 meters per second divided by 10 meters per second squared means that it keeps going up for just 1.2 seconds longer. All right, how much farther is that? Well, the distance is the area under the curve, and that's a triangle again. So 1/2 base times height. So let's put in what I know, 1/2. The base is 1.2 seconds. The height is 12 meters per second. All right, so then what we're going to do is we're going to take, 12 times 1.2 divided by 2, and we get 7.2. So it travels another 7.2 meters as it's going upward. All right, and so I guess one thing to note that this acceleration was in the downward direction. That's what makes this a negative slope, which makes it slow down from 12 meters per second. To find the total height, then we're going to add the heights from the two different parts. So that total height is going to be, we found that it was 12 meters as the rocket was had the rocket engine on, and then we have this 7.2 meters here, and so that total height that it's going to get to is 19.2 meters. Time for you to solve something. So we have we got a lighter rocket, right? So we were able to build the same, we're able to use the same engine, but with a lighter rocket. And so with a lighter rocket, 100-gram rocket, what's going to change here, right? So I want you to figure out, just figure out in this case, how high does the rocket go? So you're going to have to think about how high does it get when the rocket is on, and then how high does it get until the rocket turns around, and add those two together. So pause the video here and give it a try. All right, so force diagram. Going to start with the force diagram. So this force diagram is similar to what we did before, but Fg is only 1 Newton now. The up force is 4 newtons. So we can calculate the acceleration using the net force, which is 4 minus 1, so I'll just write 3. And what's the mass? The mass is now only 0.1 kilograms. So now this is a hugely different number from what we had before, because I cut the mass dramatically. So 3 divided by 1/10 is 30 meters per second squared. So that's pretty good acceleration. The rocket's still on for 2 seconds. So let's go ahead, grab a different color, do a velocity time graph. And so for this velocity time graph, I guess I'll draw it here. We have it on for 2 seconds. The slope is now 30, which is 5 times bigger than before. And we can figure out how high it went if we can figure out the velocity first. So based on things that I've written before, I'm just going to jump from the slope equation to here. Velocity equals the acceleration times the time. So the velocity is going to equal 30 meters per second times 2 seconds. So that's 60 meters per second. So that's going pretty fast. Okay. So then what about the area? Well, the area is going to be that 1/2 base times height, since it's a triangle. So the base is t, the height is v. And so let's substitute those in. So 1/2, 2 seconds times 60 course, those 2's cancel out, so that distance is 60. All right. So while the rocket engine is firing, it goes up 60 meters. So now let's look at what happens once it turns off. So once it turns off, actually this graph's going to extend and go down, but I think for simplicity it's going to be easier just to draw that section of the graph. Let's draw it down here. So after 2 seconds it's going to slow down, right? So my velocity is where? Right there. So 60 meters per second. We don't know how long it's going to take, but now that it's in free fall, the slope is 10 meters per second. So let's go over here and figure out something about that, right? So slope equals change in velocity divided by change in time. I can solve for the time, so I will. And so the velocity was 6 meters per second. The acceleration due to Earth's gravity is 10. So that time that it takes to get to the point where it slows down is 6 seconds. And that kind of makes sense because the acceleration here was 30 meters per second, and now it's 10 meters per second in free fall. So that's cut in third. So what that will do is it'll take 3 times longer to slow down coming from the same speed. All right, so then we want to know how high it went. So the height is going to be 1/2 the base. So let's just write the numbers in. 6 seconds, and the height is 60 meters per second. So 6 times 6 is 36, add a 0, 360. And so half of 360 is 180 meters. So it takes a while, right? So you had this high acceleration over a short amount of time. So it got to a high speed. And then it takes a while for it to slow back down to 0. And so what's the total height? Take these two, add them together, and that total height will end up being 240 meters. All right, so keep working on these problems, and the more you practice, the better you'll get.